All right, let's start. Yeah, so what I did was to go through the chapter vectors, kind of very quickly, then try to do some exercises. Then I went back, tried to fill in some gaps. And the main things to pay attention to are the ones that I'm going to present first, and to be very quick, hopefully. The first thing is it's more of like a tip. So you could learn R starting from tidyverse and dplyr and things like that. But then there is other people who learned R starting from vectors, from the base R basically, and everything has its own advantages. But the good thing is that if you really understand how the vectors, how R works with vectors, then it's easy for you to create functions and understand some functions, because R is more of like a vectorized language. So that's one thing to note. Um, okay, then this I have this picture here which shows the what I might call like the hierarchy or anatomy of vectors and different vector types. So you have the unique vector type, which is null or like empty or something like that. Then you have these other kinds of vectors. So we have what we call atomic vectors, and examples of these include logical, numeric, and character. Numeric can either be integer or double precision numbers. Then you have the list. The only difference between the atomic vectors and the list is that the atomic vectors actually should only have one type of elements. For example, you can only mix logical elements and character elements. And but the list can have a different combination of the atomic vectors. Yeah. So then from there, I have two special um, functions that are really helpful. The first one is should be class of, which I don't have here. There is a where you want where you could you can call that function, that helper function, and you can tell whether the given object is maybe of vector class of type class of type vector. Sorry, and this applies of course to every other thing like maybe like a ggplot object or something like that. But you can also have the type here for on a vector. So if you call the type function on a certain vector, it can tell you whether it is character or it is logical or integer. I mean, or numeric. And there is other helper functions in the um, par library, which is part of our tidyverse. So it's PURR, and it can tell you exactly whether something is integer, whether the vector is integer, double, or character. We might see some of those functions, I guess, in the exercises. Then, of course, the other one is the length of a vector. How many elements are in your vector? And this can also apply to list, basically. All right. So that's it for now. But one thing is that sources the foundation of the basic type of data structure in R is a vector. So everything builds on top of a vector. So R doesn't really have scalars because every number or what we call a scalar is actually a vector of type of length one. And so from the vectors, you can build on two lists. Then from lists, you can build on two data frames and things like that, and more complicated structures. For example, maybe you can even think about tuples and stuff like that. But okay, so let's jump into the exercises. Just now, I don't know, I think it would be better for me to, I'll be switching back and forth this document and R because we might need to try out certain things that would be more interesting. I'll switch right now. I think that would be better. All right. So just please ask any questions, or if you want to try out something, then we can try it out. I think that would be more interesting than me just trying to show something. So anyway, the first exercise is this one here, number one, and they want us to describe the difference between is.finite and negation of is.finite. So here, of course, for me, what I did was to try out these functions and see what happens. But even if you try to interpret it, basically, it's going to be, it can also still give you what it's supposed to do. But what I got was is.finite is a helper function that tries to check whether a vector is finite. But if you look at is.infinite, is actually going to try to first find out whether an element in a vector x is non-finite, then it negates that. So basically, it goes back to trying to check whether x is finite, if I remember this correctly. Okay, I need help here.
I think one of the things also is NA. So
yeah.
Like is NA, like we can't say if it's finite or not. So the result should be NA. And again, infinite, we can't say if it's infinite or not. So I think that's the case where like is finite X and not is infinite X will not be equal if X is NA. But yeah, we can check that.
Yeah. So we can try it out here.
So if you do is.finite.
Yeah, what was the short code for the R chunk?
Shift, Alt, or Option I.
Oh yeah. Shift.
I think. Shift or Shift Command.
Yeah, let me see. No working.
One sec.
All right, let's see. I need to remember that. Okay, so let's just create one like a vector here. So we can have NA. We can just have that one there.
Yeah.
And minus infinite and infinite. Probably that should be fine. Then we check out is.finite x. I'll just try to cheat here and run this.
So it was Command Option I.
Command Option I. Okay. All right. Great. Yeah. So here, if you look at the two functions, is.finite actually the main focus is the NA to see how it treats the missing value. So is.finite actually does not take into consideration the NA.
Yeah, because you can't know, right? Like the NA, basically, we don't know what this number is. So we can't say whether or not it's finite or infinite. So that's where the only difference is between them. So if you look at like 1, is finite of 1 is true, and is infinite of 1 is false. So when you do the negation with the bang, the exclamation mark, then that's also true. The only problem is NA. For either of them, it will give like the same result because we don't know if it's finite or infinite.
Yeah, and basically, these functions here, the logical functions being applied on NAs or nuns, they are on the side of caution.
Yeah.
Like just take the false, like they don't know, so rather non say.
Yeah.
Okay. We might need to borrow this actually for another example later on, another exercise later on. All right, okay. So the second question is this one here. They wanted us to read the documentation or source code for the dplyr near function, just to see what it does and how it works. And basically, so we have this part. This question is about the fact that the doubles and integers are actually different. And maybe I could try to do that. I haven't tried this one out. That should be fine, right? There was a good example in the book. I can try to bring up. Let's see. Yeah, so is it this one here? No, this one here. So basically there is some level of precision. Doubles are actually approximations. That's why you find that you have such a weird thing happening here. The square, when you take the square root of 2 and you square that, then you subtract 2, you get some difference, which ideally shouldn't really be there. But so when you actually try to use the equal sign here for such situations on doubles, then you won't really get the right result, especially if you're trying to have robust functions. But the option here is that right now, at least currently, we can use a helper function from dplyr, which is near, and can easily capture the level of tolerance, numerical tolerance that is feasible for these comparisons. So if you just look at this function here, dplyr near, you could see the source code very clearly, and you can just see that here that it takes two values, x and y, and checks whether their absolute difference is less than the tolerance. So I learned something that this tolerance here actually is more like it's more like some values in R, and you can check it out. You can write out my .machine double EPS, and it gives you some value. You can write down maybe something like this, and oh, sorry, just double or integer, and you see what happens and stuff like that. So there's a lot of things that happen with this machine dot machine, and there's so many things as you can see here. Talk about the number of digits you could have, rounding the digits for long doubles and things like that. But I don't think most of it will be very interesting anyway. Yeah, so basically this is what NIA does. Takes two values, two numbers, x and y, and checks whether the absolute difference is less than the tolerance. In this case, the tolerance for this machine is actually this value, if you put it in. Yep. So any questions?
Nope.
Nope.
All right. So the third question here was about they was saying that the logical vector can take 3 possible values, and they wanted to know how many possible values an integer vector can take, and at the same time, how many possible values a double vector can take. And of course, you could Google this and see. But basically, the first thing we need to know is that a logical vector has 3 possible values. Logical is either false or true, but we have a special value, which is NA. So this one here takes only three possible values. And that's pretty easy. But now, when it comes to the integers, actually answering this, we need to come from the from the point of view of the bits. How many bits are used to represent integers? And in this case, if you read the documentation of 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 R, they will show you that actually they use 32 bits to represent the integers. And this just means you do some math and just comes to this number here of possible values. And this number includes the reserved special value, which is NA integer. And ideally you can take this as NA, but it's to be specific to integers, this is NA underscore integer. And like I said, this dot machine has a lot of things. And you can see if you use dot machine integer dot max, you can actually see the maximum value R can use to represent, R can represent on a given machine. So basically here, if you add like 1, am I adding integer? So if you add 1, then it shows you that it's not possible. Basically, it doesn't know that. And you can also do the same thing for minimum, things like that. Yeah, this is not really so much fun unless when you're dealing like with some kind of big numbers for some industries or some jobs. But so basically, we do the same thing for doubles. So doubles more of like you multiply the 32 bits by 2, and you get 2 to the power 64, and this includes actually some special values, which is NA, non-inferior, infinite, and negative infinite. So from here we can also see the difference between integers and doubles in the case of in the case of these 3 new special values: the none, the inferior, the infinite, and negative infinite. And of course, this NA here, you can call it NA underscore double if you want. Yeah, so this was fun to find out actually. So any questions about that?
No. So I guess when you've added 1, you in effect, because you hadn't specified the L, you turned that into a double, right? Which is why you got the next number.
Yeah, that's right. That's right. So
Interesting.
turns it into a double.
Cool.
Yeah, so okay, yeah. Now there was some other stuff here which wasn't that fun though. They wanted us to brainstorm some functions that allow us to convert a double to one integer. And yes, and how they differ, basically. So I came up with some. I think I've used, for example, you can try to find a flow. Let's try this one here. We're trying to convert the double. Let's see. Command Option I. Perfect. So let's see, our double is double. Okay, 2.567. Right. So we can try out flow of X. Then ceiling of X also. That's okay. Not sure how truncation works. I think it has. Let's try that for now. Yeah, or truncation just works just fine. So here, basically, we've turned. I think we need to test whether is. What is that function?
I think you have 3 R's.
Sorry? 3 R's.
3 R's in per, yeah.
Oof. Oh yeah, nice. Oh, so it turns into a double actually. That's true. That's true. Okay, so the ceiling also does the same thing. The truncation also does the same thing. And as integer, but that's weird. Because basically this flow is not turning it into an integer. We want it's not true, is it? What it does, how it looks is actually an integer, but the type is still double. That's really
So
weird.
I guess you can then wrap that in round brackets and go as dot integer.
Oh yeah, so I think as dot integer would be much better. So let's do this. Hope I don't get any errors from this copying and pasting. So yeah, so that works very well. I think the strongest one here actually is as dot integer.
So what's the difference between trunk and floor?
I actually don't know.
Okay.
I actually don't know. Let's see. Rounding of numbers takes a single numeric argument x and returns a numeric vector containing the smallest integers, not less than the corresponding elements of x. I don't know what that means. I don't know what that does actually. Let's see trunk.
It's about negative numbers apparently. So trunk takes a single numeric argument x and returns a numeric vector containing the integers formed by truncating the values in x towards 0. So if you have negative numbers, they'll differ in terms of where the floor goes.
Okay, so for example, if you have, let's see, minus x. Let's put it here, leave it there. X. Is it like that? Do you see this? What do they mean by that? I don't understand it.
So for example, like the example I found, let's create a new x, make a vector, and we can compare the difference between floor and trunk. So if you do like, I don't know, minus 3.5.
Okay, let's do this.
And minus 2.1, and do a couple of like plus numbers.
Minus 3.1.
And like 2.5 or something.
Okay. There we use flow.
No, but let's just print it. Like, can you print?
Yeah.
So that we see the difference. Like trunk, you know, let's create a vector like x equals, or not equals, whatever, x arrow. Yeah, and C and open brackets, and then we can do like minus 3.1, minus 2.5, like some that will basically round up and round down.
Okay.
And a couple of like positive numbers, which we can expect, I don't know, like 1.8, whatever.
All right, do that.
Yeah.
1.2.
Cool.
Okay.
You've got a minus in 3.1.
Sorry? Yeah. That's not good. Okay.
And if you just like, instead of saying equals equals, if you just do trunk x and then in a new line floor x, we should be able to.
Okay, yeah.
Let's see that.
Why is it doing it the same way?
No, they're different. Look.
Yeah, this one float. Oh yeah, I understand now. Yeah, the difference is in the negatives.
Yeah.
Yeah.
So floor, so minus 3.1 is between -3 and -4.
Yeah.
-4 is less than -3. So floor goes directly to the lower number.
Yeah.
Therefore, you went from -3.1 to -4, whereas trunk goes to the number closest to 0. So in essence, it does the floor on the like absolute value, if you will. So
Yeah.
-3.1 goes to -3 because -3 is closer to 0 than -4.
Mhm.
Which is a bit
Okay.
counterintuitive, but yeah, good to know.
Yeah, but for me, for me, I just take it that trunk just removes the you know, the 0 point, the fraction part.
Yeah. But like
Okay.
if you floored -3.1, would you expect -4?
If no,
I
I
would have
mean,
expected -3.
actually, I would expect -4 if you approach it from the number line.
Yeah.
You know, so like for me, how this is how I learned math. It's more of like I always have to draw the number line.
Mm-hmm.
Then from there it becomes very intuitive for me.
Cool. Yeah.
But the thing is that if you're working on it like with mixed numbers, both positives and negatives, you never really think about the negatives actually.
Yeah. Yeah.
Hmm.
Cool.
All right. Trunk. Yes. So the next number is it's about some functions in read-r package, which is about reading in the data. And they want to know which functions allow us to turn a string into logical, integer, and double vector. And here it's more of like when you're reading in the data, you can actually specify that I want this column to be passed as a logical vector. I want this one to be passed as an integer and whatever you want. So these are the functions like I found. So there's one for logical, integer, and number, which I think should do the magic for double. And you can actually try this out because we know that tables or whatever all data frames are actually going to be lists of going to be vectors and lists of vectors. So you could actually try something like base. Let me try here. I. Okay. So try vector first. False. 0. True. Okay. So basically, what this is something like this is what it does. It has turned the 0 into into a logical logical vector or logical entry that is false in this case, and it would do the same thing for if you have integers, if you have past numbers. And I think I read somewhere that there is a difference between past integer and past number, and I'll just show you here. Okay, so just copy this. Okay, so let's just try these two, pass integer and pass number, to see the difference. What do I have?
It's the ABC, I think, in the
yeah,
in
yeah. So this is what it does. So pass integer does not really cannot really grasp anything like points and commas and numbers. So it gives you like an error or a failure. However, actually, if you look at pass number, it does something. Oh, what is it doing? 0.3. This is not what I want to see.
I think that's coming from your pass integer call.
Oh, really?
I think so. If you comment it out, maybe it doesn't.
Yeah, let's try to see that.
Yeah, so it's from the integer.
Okay, so it's giving the error, but that's not what I want to see. So let's just do another one with a pass number. That's a very detailed error. Yeah, so pass number actually would actually pick out the numbers from whatever you have, like this.
Mm-hmm.
That's a advantage I saw for pass number over pass integer. So pass integer actually brings you some errors like we're seeing right now, and the ones which it cannot capture, it gives them as NAs.
Cool. And what happens if you, instead of 0.34, you have an integer as well in the first position? So if you just do, I don't know, 34.
So here, yeah, 34, it should be fine. So
now I meant for the next one as well, like for the pass number.
Yeah.
Okay, so now they're all integers because there was no double in there.
Yeah. Yeah, I see what you mean. Yeah, that's true. Oh, that's very true. Actually, I didn't thought about it.
Cool.
Yeah, nice. All right. So the second part of the exercises, it's about, this is something I think we did last time, about what does mean with some kind of logical function do, and some kind of logical function do. So we have mean is dot nax, any vector x, with certain numbers, for example. Then we have another one for sum. Is we want to get the sum of the elements of x that are non-finite. Yeah, and basically the mean gives you the proportion, and the sum gives you the number or the count of those elements that are non-satisfying a certain condition. In this case, we have finite, non-finite. So you can skip over this, I think. Yes. So then the next one is about reading the documentation of is.vector and is.atomic, and trying to find out what they actually test for and how they differ. And this one here wasn't so clear. I had to read it over and over again, and I don't think I got it right now. Yeah, but what I understand is that so this one here, I got it from the documentation of is.vector. If I just do help question mark is.vector, it said that is.vector returns true if the object has attributes other than names. So the vectors have certain attributes, for example, names, or they have like they have the names, then they have the type, for example, and what else? Now you can add whatever attribute that you want to add, basically. But the main one is the name. So what I mean is that if you have name vector is equal to let's see, C12, and then I have attribute of name vector. Come on. What happened? Ooh. Oh,
Looks like
sorry.
we missed an argument.
Yeah, so it's not like that. That is for changing. So here I need to say attributes. So it doesn't have any attribute. That's weird. Okay, let's add an attribute. So I can say attribute or vector code. I don't know. Let me call it Alan. Is equal to. Now I've forgotten how to change it. Is equal to yes. Let's see how that works. And if I actually call the attributes, then to have this. And we know this is a vector, right? And let's just try to do is.vector on my newly created vector names that tells me that it's not a vector. And the reason is that it actually has another attribute, more than one attribute. In this case, the one I've added, which is called Alan. But I think, if I remember correctly, if I use this one here is atomic, then it should be true. It's an atomic vector. Oh, I don't know. It's really something weird that I found. But what I also remember is that the atomic vector kind of thing is very, very useful when you're actually trying to manipulate and create functions, especially also what they call like S3 objects in R. But I don't think right now we need to really worry much about it. But if you're creating more complex packages and functions, then you might need to really actually pay attention to this kind of thing. So that's what I have to say about this one here. I don't know whether you guys have something to add.
No, not me.
No, thank you.
Yeah, so I just put this picture here just to see, but I don't think it was passing on anything actually. But just put it here just to maybe we might have needed it, but I don't think we need it for now.
So the name vector you've just created is not a vector, but it's atomic.
Yeah, exactly, exactly, and it's not a vector because I added the new one here. So if I just take it back to what we had before.
But what is it then? What happens when you look for its like type or class?
Is
it a list now? Is it a
class? Let's say class. Well, at least you'd have that attribute class numeric. Oh, that's not good. We shouldn't use that. Type of, yeah. Let's use type of. Double. Okay.
Double.
Why is it double? Why is it?
Because you put the values are double.
Oh yeah, numbers, right? Yeah, they don't integer. That's right.
But what? Okay, how do we find like the type of the object name vec?
Yeah, type of the object.
I don't know. Can you do like question mark name vec? Can we get anything from that?
That's it. That'll be fun.
Now.
Yeah.
It may not work.
No document.
Okay.
Yeah, I really want to do actually what you're saying. I don't know what.
Do you want to try the thing it's suggesting with double question mark? I don't know if that will.
Let's see.
Give us anything.
Nothing.
No. Okay, cool.
Oh, interesting. Let's see. So I think, but now if I say, when was this?
It is dot vector. Maybe is underscore vector is from another package.
Yeah, this is from another package. This is from the power package, I believe. So this works better than than this one here, is dot vector. Yeah, and this is also, I think the one the helper functions from base R actually can easily act funny.
Yeah.
So you have to use them with caution.
Cool.
Yeah. Right. Nice. Yeah, we have another part from base R and par. So basically, if you have a vector, you can name you can add names to a vector, to the vector elements, just like we saw some time back when we were talking about factors and factor labels. This is something similar. Basically, we want us to compare set names, which is from base R, and par version of that, which is set underscore named. Basically, it's basically the same thing. However, the only difference that I found was that with set names, the what I would call the new version, the one from par, you can use a function to actually transform the existing names. And I put this as an example. So if you have like m is equal to 1 and f is equal to 2 as a named vector, I can actually convert those to uppercase, either with that or by using a tilde and write the function and an element. This element is more of like every element here is you can use a dot to communicate to the function. And actually, this will be very useful later on when you start thinking about writing your own functions in to go on with the tidyverse functions. But yeah, so basically, this is what you get. The first one you get upper to upper. The second one you get that, the same thing basically, and that's a difference. But the other way, they work the same way. And the other one I found was set names allows naming vectors, allows the naming vector to be shorter than the vector that you are naming. Whereas set names, which is from the par function, par library or package, gives an error. And don't know if I could try that. So we could try that and see. Okay. I put that, I have that, and one, two, M, F, O. I guess that should be able to work.
But here your naming vector is longer than the vector to be named.
Yeah.
Okay.
Yeah, exactly.
But yeah,
just to see this error here. This is quite annoying that they don't split it up. So you can't have two things after one produces an error. If I run that, oh, working. What's the problem?
no, as I was saying, your name vector is longer, whereas I think it should be shorter. So if you do C like 1, 2, 3, 4.
So if I do like 3, 4,
so, and 4, like make it longer.
Yeah.
Let's see if that works.
Yeah. Yeah, that's right. So basically, you don't really have to name every element. You just have to provide just a few of them. But yeah, but then the one from part gives us an error completely. Yeah. Nice. Right.
So how would we go about it? Like if you wanted to skip the name of the others, do you know how you could do it?
You mean the name of this one here?
Yeah, like in the per version as well.
I have no idea actually. No, I have no idea about that. I don't think it would work.
Cool.
Yeah.
That makes sense.
Because some options that they use, like in the power, in the tidyverse versions, you maybe use some kind of like replicating the vector, but that won't work here. It won't provide us with a nice result.
Cool.
Right. Okay. Yeah. So then there is some fun functions to write. But yeah, so here there is a writing function that takes a vector as input and returns different things. And the first one was returns the last value, and they want us to decide whether to use this one here, a single block bracket or double block bracket. So now here, whenever we see block brackets, we think about subsetting, and block bracket is actually a function itself in R, which is used for subsetting. So here, the thing is that the double block brackets actually extract a single element, and they drop the names of the elements. And that's a major difference, or if not the only difference. Whereas the single block bracket subsets and just can select the nearest level below the main level. I don't know how to explain this, but yeah, we might be able to see that anyway. So this function here that I wrote is trying to get the last value of a vector. So it takes the vector, and basically what it does is that it gets, I'm using the length of the vector, so that whenever you have any value here, let's just try to see how it works. So this is how it looks. I have a vector 1, 2, 3, 4 up to 10, and I'm extracting the 10th vector. And the magic is just here, actually. So I had just put some condition to make it a little bit robust. Probably not really needed here, but yeah, you could do whatever you want anyway. So I just have a function here. An if statement saying that if the length of the vector is actually positive or greater than 0, then you do something. If not, you just return the same vector. And still in the book, in the book where we're talking about vectors, they talked about this kind of if statement, for example. So what it does is this if statement actually returns a true for any value greater than 0, for any value of length greater than 0. And it will return a false for any value less than 0. It's always wise to just write it out completely so that you know, and people can follow your code. So this should be able to work the same way.